Okay, welcome everyone. It's Wednesday. Just can you see my OneNote screen? You can hear me. Is that right? Great. As usual. Okay, this is from last time. I just remind you, you've worked on that homework quiz. Folks are asking some stuff on Campus Wire about that. That's great. One of those problems is a little trickier than it involves a few different time periods, et cetera. So keep working on that. Obviously, we'll go over it in class on Friday. In addition, on Friday, though, just as a reminder, I've asked you to carefully read this paper. I think you'll really enjoy it. It's a unique perspective. It's unlike one you're ever probably going to get that you've had before, okay, about ways in which you can address environmental problems without legislation and what the downside of legislation is, okay? So there's a short reading quiz associated with that. And there's also an example of, or at least we're going to apply that to this example here in Kern County, where I give you a short video discussing a conflict between an pistachio cotton farmer on the west side of Kern County, where they are impacted by groundwater contaminated from an upslope oil drilling operation. Okay, it's a pretty neat video. And so just read that or watch that. So again, 3 things for Friday. And any questions though before we begin today? Okay, so for today, I have, I graduated high school in 99 in Cincinnati, and then graduating, I believe, you must have been 98, clearly. John and Justin Kreinler, who are now I'm going to say co-directors, president, founders, et cetera, of Exaquest Carbon. So fairly new organization, but I was lucky enough to find them and just kind of stumbled across them looking at a couple things on LinkedIn or Facebook or whatever else. And then they graciously agreed to explain what Exaquest does. You've had some idea, and they've also appreciated your feedback based on their website. And without further ado, I'll let them take over, and I'll stop sharing my screen and go from there.
Okay, and well, I'm John Lynn. Hopefully you can see Justin on the screen. Just wanted to thank you, Damien, for inviting us. I am about to probably screw up this screen sharing business, but let's see if can make it work. So I'm going to try to share these slides and then make them full screen. So tell me if that goes full screen for you guys.
Yes.
It does. Okay, great. And does it advance?
Yes.
Okay, good. All right, then we're good to go. So yes, Damien stumbled upon our website. Justin and I are directors, I guess you could also say co-founders of a nonprofit called Exaquest Carbon. We are engaged in scientific research that we will describe to you as this presentation progresses. And we also have in our title, negative emissions technologies, because that's what we're involved in. And I think this is a major issue of interest, as you may have gotten a sense when you took the survey. And speaking of which, thank you for taking the survey. There are 29 out of 35 who responded. The purpose of this was to get us a sense of how you feel about climate change. But I think now you can, looking at these answers, you will get a sense of how your fellow classmates think about climate change. And I think this is something we don't really talk much about in life in general. We all know that it exists, but we don't know how other people feel about it. So I'll just run through these results. I have a couple comments, and then we'll get to the substance of the lecture. So we asked, how negatively do you think climate change will affect your life? A 1 meant so no net impact, and a 10 meant your life would be in danger. And you guys came in with a mean answer of 5.4, the median was 6. So, it's a moderate level of concern. We also asked, from a broader perspective, how negatively do you think climate change will affect humanity in your lifetime? So all of humanity. And interestingly, these scores are 1 full point higher on the mean and the median, suggesting that you think it'll affect other people a little bit more than yourselves, which is very common, by the way. That's nothing to feel bad about. And then relating to today's talk, we have these ideas of getting to net zero CO2 emissions. We asked how much confidence do you have that we'll achieve net zero CO2 emissions in your lifetime? And I apologize here. We should have set the scale of 0 to 10. I guess I wasn't just thinking. But all that means is that each point increment is just 11.1%. So your mean response was 3. So you're not very confident that we're going to get there. Median was even lower, only a 2. Although there was one person who was extremely confident. I'll have to look that person up. Okay. We had 2 other questions. What, if anything, makes you believe that humanity has any chance of achieving net zero CO2 emissions in your lifetime? I would say if it's possible for Professor Park to sort of remove the names from the responses and share these, it would be great, because I found them fascinating. I think there's a really interesting mix of extreme pessimism, cautious optimism, and then some real optimism. So it kind of mirrors the population at large. I think we're kind of undecided on this issue. And then, relating to today's lecture, we asked if you're familiar with any of these negative emissions technologies. I should say this is not the full universe of negative emissions technologies, but it's a good starting point. And what I found interesting was that almost all of you sort of get the idea that growing trees can store carbon. So that's well known. Biochar is known by very few of you, and the rest of them are kind of in between. I guess soil carbon storage comes in about 50%. So hopefully you'll come away from this lecture understanding a little bit more than you did before. Okay. Oh, and Damien, if you catch me drifting too far over time, just give me a shout. Maybe at, say, like 20 and 30 minutes, just let me know what's up.
20 and 30 minutes left?
Or I mean, like after I've been going for 20 minutes or 30. I'll get my clock out here.
Okay.
I'll keep an eye on it too.
And by the way, please, I'm going to monitor the chat. I forgot to say this, but I'll keep monitoring the chat. So please chime in, and I can, yeah.
Yeah, feel free to interrupt. I mean, we've timed this lecture at something like 35 to 40 minutes. So we're really hoping to have time left over at the end. And yeah, again, if you catch me drifting long, there's nothing that important about what I'm saying. Okay. So climate change. I'm going to say something controversial. It's not going away. And hopefully some of you have seen this graph on the left. It's what's called the Keeling curve. It's the longest continuous measurement of CO2 in the atmosphere that we have, at least in the United States and the Western world. You can see that in the last 60 years, we've increased the atmospheric concentration of CO2 by about 100 parts per million. That translates to about 1 trillion tons of CO2 additionally that's in the atmosphere. So that's a lot. And I'm not giving a lecture here on the effects of climate change. I think we can all accept that CO2 in the atmosphere causes climate change. So another plot for you to look at. There are 2 things going on here. You have gigatons of CO2 emissions on the left-hand y-axis, and then gross world economic product on your right-hand axis. And what you're seeing is that there has been a little bit of a decoupling of economic growth from CO2 emissions. And you're the economist. I was an econ major a long time ago. Is that a universally positive development? I'm not sure. But what I would urge you to look at is the open circles. So this is actual CO2 emissions for the past 30 years or so. And you can see that from about 1990, we were at about 22 gigatons of CO2 per year. And you get up to 2018, 2019, and we're hitting like, say, 35 gigatons of CO2 per year. So we've increased our annual emissions by about 50% in the last 30 years, despite having solar panels, wind turbines, switching to natural gas. So this problem is not going away, and we're not particularly solving it at the moment. I'm going to say something else that's a little controversial here, and I really hope you push back against this a little bit. But I believe that simply reducing CO2 emissions is probably not going to save us. We could have an entire course on this issue, why that's the case. But I'm going to boil it down to about 3 factors, or 3 sets of factors. The first is energy storage, right? So right now, the world runs on about 80% fossil fuels. We would like to replace it with wind and solar. I saw some of you mention nuclear. There are many other forms of energy storage and nuclear as well. For various reasons, they're not that, people aren't clamoring for nuclear. So what people are clamoring for is wind and solar, which we all know are intermittent. Wind doesn't always blow, sun doesn't always shine. And so among the many ways to store energy that you could generate renewably, most people are gravitating towards batteries, which are just stored electricity. And I will tell you that in terms of cost and energy density, batteries are not up to snuff yet. And the easiest way to understand that is to just realize that there are no battery powered airplanes, there's no battery powered heavy duty trucking, the things that require lots of energy in a concentrated form, the batteries can't hack it yet. And this is, I think, this is a controversial thing, but I will say, I think that may be a physical problem. This may not be something we will solve with further innovation. Okay, a couple other major factors that should give us pause about just reducing our way out of this problem. We have industrial agriculture, which is, deforesting the Amazon and Southeast Asia at a shocking rate. It results in massive soil carbon losses. And this is not in process of changing. I would say industrial agriculture continues all over the world. So does economic development. We're in a world where economies want to grow at 2 to 3% per year, and that is just more of everything every year, more production, more consumption, most of it resulting in more CO2 emissions. And although population growth is not increasing, population is not growing exponentially, it is still growing. It hasn't plateaued yet. It is not shrinking. So we're heading from about 7.7 billion people today to about 10 billion in 30 years. And on top of that, we can't rely on just nature itself to suck up tons of CO2. Nature's own mechanisms remove CO2 at very slow rates. So if we want to solve this problem, we may have to intervene ourselves. And this brings me to another controversial claim for some folks, which is that we are going to have to remove CO2 from the atmosphere. I think this is becoming less controversial as time goes by and we continue to fail to stop climate change. But here we go. How can you remove CO2 from the atmosphere? So this is from a National Academies of Sciences study on negative emissions technologies from about 2 years ago. I'm not going to talk about coastal blue carbon. That's kind of a small potatoes solution. But the 6 that I mentioned are all listed on this figure. So let's start with direct air capture. That's this machine in the middle with a bunch of fans. And that's pretty much what a direct air capture machine looks like. You suck in air, your 400 parts per million CO2 gets absorbed. You then collect the CO2. You compress it to many, many times atmospheric pressure, and you're going to shoot it underground into rock formations. There's a slight variation of that. It's called biomass energy with carbon capture and storage. The difference there is that instead of capturing CO2 from the air, you're going to take biomass like wood and plants, you're going to burn it. So you get energy, you release CO2, capture the CO2, compress it, shoot it underground. Afforestation and reforestation, you all seem to be very familiar with. I'll just note that afforestation means growing a forest where there wasn't a forest before, and reforestation is bringing back a forest that used to exist. Soil carbon storage is interesting. It's this idea that through agricultural practices, cover crops, composting, you can increase the soil carbon content dramatically. And I'll just note that organic compounds are constantly decomposing in the soil. So there's a little bit of an issue of how permanent that storage is. We have a method called biochar, which is interesting in the sense that you take biomass, you heat it in the absence of oxygen. It's almost like burning it, but without oxygen. And what happens is that you get a kind of ash product, which biochar advocates will say is very good for soils and crops. And so you can just put that in the ground and it's not going to decompose for a very long time. And then one that I think you may not have heard of, at least in the survey, many of you hadn't heard of.
John, can I ask you a question there?
Yes,
you say for a very long time for biochar. What does that mean?
It's unclear, right? Nobody's done a 1,000-year experiment with biochar. But biochar is, for any, this is maybe drifting into a little chemistry here. It's not graphitic carbon, right? It's not pure carbon, but it's also not, it's in a form that is more difficult for bacteria and funguses to decompose.
Okay.
So think of it as like charcoal bricks. And you can bury those and your charcoal bricks really aren't going anywhere for quite a while.
Okay.
But it's a controversial claim, this idea that it will last for 1,000 years, because obviously no one's proven that. Okay.
And actually, I'd like to ask about the soil carbon too.
That's right.
Is for soil carbon, what does that mean? Like if you expand and cut down an acre of forest and you just use regular farming practices, that obviously releases some soil from the trees as they decompose as well as from the soil. But if you say have a better cover crop or change your practices, you might be able to reduce some of that carbon leaving the soil. Is that the idea?
That's correct. Yeah, a lot of it is switching to no-till methods. So tilling the soil sort of churns it up and releases these. People use this term humus. It's like or humus is a form of carbon that is resistant to decomposition. It tends to exist in deeper soils, and so the idea is that your various agricultural practices will encourage carbon to become humic in deeper depths of soil. So people talk about regrowing grasslands, and the roots will pump carbon into the soil, avoiding tilling, composting, these kinds of things. Pasture practices, allowing animals to kind of rotate through pasture land, and then their droppings get incorporated into the soil. There are a lot of methods out there, but I would say they're on the side of being relatively untested. We're not quite sure how well it works. And then there's this accelerated chemical weathering, which I think is pretty fascinating. It's think of lava. Like when lava comes out of a volcanic eruption, this is essentially rock from the Earth's interior that is being spewed up onto the surface. And those rocks contain a lot of silicon and magnesium and calcium. And over time, the silicon gets replaced by carbon dioxide. There's like a replacement reaction. And so that process stores CO2. And what people want to do is accelerate that quite a bit by finding volcanic rock and then turning it into powder, grinding it up into powder. Okay. Well, I'm glad you asked all these questions. Are there any more? I mean, I think as far as the negative emissions technologies themselves, now is a good time to ask. No? Okay, we'll move on. Okay, well, I've made these aggressive claims in the previous slides, but there is smart money that agrees with me. Smart money is betting on this. So we'll, let me see if I can bring up a little laser pointer here. We'll start in the top left here. So this is about a year ago, oil companies investing in a company called Carbon Engineering. I would say this is the best known direct air capture startup. They're being funded to the tune of hundreds of millions of dollars. You go down, Amazon has a $2 billion climate pledge fund. They've just announced their first set of investments. Carbon Cure, for example, is a company that puts CO2 into cement. Microsoft has announced $1 billion that it's going to invest in this. And Shell is putting its money on reforestation. So I'm not the only one saying this. And I would say in academia and among climate scientists, this view is becoming pretty widely held. So this takes us to a question, probably the most important question is that will negative emissions technologies actually be able to remove enough CO2 to stop climate change? And I'll tell you straight out, we don't know. If you guys want to troll around on YouTube, there's a climate scientist named Kevin Anderson who is extremely down on negative emissions technologies. He's saying we're making a huge bet on technologies that don't work yet, and it's a huge risk. But yeah, it's true. We really don't know. But I think when I put this lecture together, I tried to intellectually break down in my own mind, well, but we don't know for sure, but what are some factors that will tell us, give us a hint as to what might work? And these are the factors. So first and foremost, you have to look at the physics of a technology, like how efficient is it? Ideally, you'd like a process that magically captures CO2 with no effort on our part and then keeps it stored forever, again, with no effort on our part. That doesn't exist, so all solutions are kind of less desirable versions of that. Profitability. We live in a capitalist world. If your process makes money, it's going to be the one that gets used. This idea of technological breakthroughs. I mean, we're in Silicon Valley. There is this idea, a lot of optimism among people who fund these types of technologies that if I just give this group of smart scientists, $100 million, they'll figure something out, right? Even if they can't deliver today, they'll deliver 10x in a year or two. Well, that's something to consider. I mean, are we allocating resources wisely if we're counting on breakthroughs? And then I think something that is particularly relevant to your class is this idea of ecological impacts. You're going to be removing gigatons, billions of tons of CO2 from the atmosphere by deploying processes at huge scales. Can you do that without harming the environment? And this is very much an open question. Every technology struggles with this. So let's think about physics first. And in my mind, I broke it down into three factors. you really need to consider the energy cost. How much energy are you putting in to capture CO2? Energy is important because for now, we get most of our energy from fossil fuels. So if you spend a tremendous amount of energy to capture CO2, you probably emitted just as much CO2 in that process. So it's pointless. And people will say, oh, we'll decarbonize all the energy. Well, that's a pretty big claim to make. It may happen, but in most cases, that's not true now. This idea of gas versus solid CO2. I don't know how many of you are science majors or not, but if you've ever dealt with gases, you know that it's difficult to keep them, especially pure gases, right? You know, your gas cylinders are typically stainless steel. You know, it's about half an inch thick. You want to deal with compressed CO2, compressed to like 70 times atmospheric pressure, which is what you need to inject it underground. You're talking about a massive investment in very sophisticated equipment. Whereas if you're dealing with wood chips, I mean, you can handle those in a wheelbarrow. So there's a huge technological difference between dealing with gases and solids. And then permanence. Some forms of CO2 capture and storage are permanent, others are not. And on the chart below, I've sort of coded these. Red is kind of a bad factor, green is good, and orange is kind of in the middle. So with direct air capture and bioenergy with CCS, you're looking at high energy costs, you're dealing with a gas, and although their proponents will say it's permanently stored underground, this has not been demonstrated. I mean, an expert at Stanford said to me that where they want to inject this CO2 is in old oil fields that have already poked full of holes. So they have a fundamental problem. Even if they find the perfect rock formation, you need to poke a hole in it to inject the CO2. And they just haven't proven this yet. Accelerated weathering. I say the energy cost is high because you need to grind up rocks. If you want to test this, try grinding up some rocks to powder yourselves and see how it works. It's quite a challenging process. But you generate a solid, and that solid is quite a permanent form of storage.
John, I was wondering if I could ask you a quick question. For the oil field, I know they're the ones who are pushing it because they do inject CO2 to kind of blast out oil. I wonder if you were to actually try to measure if your CO2 is leaking, the only way I can think about it would be to measure the pressure where you injected it and see how that pressure, if the pressure stays at whatever it is, that's a pretty good sign that it's not leaking. But is that, I mean, how else would you measure it?
I think you're right. That's a pretty good way to do it. That also assumes that your oil field is like a contained thing. You know what I mean? Like it has walls and your injected fluid can't be expanding outwards. You would also probably be looking for CO2 leaks at the surface. You know, I think there are ways now to track sort of cracks and deformations in geological formations. And so I'm no expert on this, but this is a question that's always asked. And the answer is always, it's 100% secure, but that answer always comes from people who have a vested interest in this. So it's very hard to believe them for sure. And the truth is we've never done this. So nature has never injected billions of tons of liquid CO2 underground. So we are in uncharted territory already. So reforestation and soil storage, these are sort of natural approaches where the carbon's being captured by photosynthesis. So the energy cost of capture is extremely low. You get a solid, which is biomass. But on the flip side, you have relatively low permanence because those forms of carbon could decompose. Biochar sort of solves one of those problems by making the char product, but at a cost of energy. And Exaquest, I will claim, can take low energy capture, make a solid, and then give you medium to high permanent storage. So this is really the problem we're attacking in a nutshell. Okay. Factor two is profitability. And what you're looking at here is a compilation of data that I pulled from various papers plotting the cost on the y-axis. So this is the cost of CO2 capture in dollars per ton of CO2. And then on the x-axis, you have your storage potential, like potentially how many gigatons of CO2 per year could you capture and store with this technology? And probably what jumps out at you is that you've got these huge ranges for direct air capture and accelerated weathering. This basically tells you that you have lots of scientists saying lots of different things and nobody really knows what the truth is. It's a lot of uncertainty. But you can see that the large potentials for these technologies make them pretty attractive. And then when you get into in the bottom left corner, you're dealing with technologies that are cheaper, but have smaller recognized potentials. So I'm only showing you the costs. And your question would be, well, that's very nice, but where are the revenues going to come from? And the truth is that right now, none of these technologies are profitable because there is no carbon price. There is no real market for carbon credits. There are some small informal markets, but not at the scale of gigatons of CO2 per year. And so, from an economics student's perspective, I think this is a fascinating thing to think about. You have a market that on its own is not going to encourage this activity. So our current system doesn't really put much of a price on CO2, and so there's no real incentive to capture it and store it. The smart money is betting that carbon price is coming, but they don't know what it's going to be. And they also don't know which forms of storage it's going to favor. So it's not just the carbon price that you set that matters, it's also the regulations. Are you going to favorably regulate one method versus another? Will you provide subsidies for one method or another? And that's just another way of saying which methods will get political support. And so I think what you're looking at here is an industry with the potential to save the world, where politics and economics will play a huge role, and the technology that wins out may not be the one with the best physics. I mean, it should be. I mean, you obviously would want to capture CO2 efficiently, but human societies may have different priorities and say, you know what, we like this other method better. And that's something to think about.
Can I ask a clarifying question about that slide?
Sure, yeah.
So just to understand, what we'd say is the abatement cost of direct air capture is the range, is the median estimate that it might be able to store close to 50 or 60 gigatons, and then the cost would be between, what's the vertical axis for direct air capture? Like, is it between 300 and something, 200?
It looks like it's between 100. I've plotted it as $100 to $300. This is actually quite generous.
Okay, so the green overlaps both. Oh, I see. They're overlap. Never mind.
Yeah. I should have chosen better overlapping colors, but I'm being quite generous here. I mean, no direct air capture company in the world is doing it for less than $600 a ton right now. All of their publications say, oh, we'll be at $100 per ton in 5 years. This is what I mean by the reliance on technological breakthroughs. There is a huge amount of projection of improvements in the future that hasn't been delivered yet.
Okay.
And this is what you're seeing in this figure. It's like the reality is really at the top end of those cost figures.
Okay. And yours is right around $35 a ton. Is that what I'm seeing?
Yeah, that's about right. Yeah, we did the calculations for it. I mean, I wasn't going to go into that in great detail.
No, that's fine. There's no need to, because I'm going to have the students do it as well. We'll do that.
Oh, okay.
So I think we'll do that.
Yeah. All right. Well, if you guys need resources for that, I've done plenty of analysis. But
okay, I'll probably grab a few things from you in the future. Yes.
Okay, great. Factor 3. So this idea of needing technological breakthroughs, and I'll just say that direct air capture and BECCS are in the position of needing major technological breakthroughs. The other ones, not so much. Yet, right now, when you see the investments that are being announced in negative emissions, direct air capture and BECCS are extremely popular. And the natural question is why? And I would say there are 3 reasons. These are just variations of, the fact that business people like these technologies. But one is this idea that you're going to own patents. You're going to own intellectual property. You're also assuming that intellectual property will be respected and people will pay for it when the world depends on it. But that's really what's driving a lot of this investment, is that companies are investing in research projects, which they're hoping will yield a patent portfolio that's extremely valuable. They are also shooting for the moon, in a sense, in essence. The direct air capture companies, and maybe accelerated weathering, they go to investors and they say, if our technology works, we'll capture 100 billion tons of CO2 per year profitably, and you'll own that, and you'll make billions. Whereas a technology that doesn't rely on such grand projections can only promise what it actually delivers. It might be profitable, but at a very small margin. So I have this possibility of $1 billion being greater than just 1 million as a sure thing. And you mentioned this a little bit, Damien, Direct air capture will use the infrastructure of the oil industry. So CO2 pipelines, the underground rock formations that previously held petroleum and gas, this is what they're planning to use to store the carbon or CO2 in. And so to me, it's no shocker that the oil companies are looking at direct air capture first. It's what keeps them relevant and could potentially become their replacement business when they stop pumping fossil fuels. Now, at this point, I have a quote here from Richard Feynman. If you don't know who he is, try Googling him. He's a famous Caltech physicist, an extremely eccentric and intelligent guy. He was one of the guys who reviewed the Challenger disaster about 35 years ago, which was when a space shuttle exploded. And his concluding line of his assessment was this quote: "For a successful technology, reality must take precedence over public relations, for nature cannot be fooled." And this is just my way of saying there is a lot of hopium, there's a lot of smoke and mirrors, there are promises flying around in this field right now. Eventually, the physics and reality will win out. So we will see who's right and who's wrong. But people make investments based on their projections of the future. So, you know, at a certain level, they have to guess. And so you're seeing the results of those guesses. Factor 4. I think this one's fascinating, especially this is a class in environmental economics. We're talking about ecological impacts at the gigaton scale. And I'll make another controversial statement. People would disagree with me, but I will say that any negative emissions technology that's removing CO2 from the atmosphere at the gigaton scale is geoengineering with ecological impacts. You are going to affect the world in a significant way, the natural world. And these have to be taken into account, better than we've taken into account the emission of CO2 from fossil fuels. We can't just replace one mistake with another. So this, I've listed here a few examples of some of these issues that these technologies will have to deal with. You could have entire lectures on these issues. People argue themselves until they're red in the face about this, but these are definitely issues. So this idea of CO2 leakage out of underground reservoirs, I would add to that this idea of massive amounts of CO2 being underground at all. Even if it doesn't leak out, it may get into the water table, you know, acidifying the water table. Does acidifying create rock dissolution? Are you changing geology in some fundamental way that it could be harmful? BECCS, there is this idea with BECCS that you're going to take large amounts of land and you're going to plant crops that grow very quickly so you can harvest them and burn them and collect the CO2. And this is in a world where we have a huge population that needs food, and these biomass crops would not be food. So you're competing with food crops. Is that going to be a problem? Accelerated weathering. You can't just use any rock for accelerated weathering. You need that special volcanic rock that's out of equilibrium. You need to find not just a little bit of it, you need to find billions of tons of it. And how are you going to make that happen? Reforestation is probably, you might think there are no issues with that, but at the scale that it's going to be required, who's giving up their land to be forest? You know, where are those forests going to grow? How are those decisions made? It's not clear. And as far as soil storage and biochar, I think this is where those techniques have a little bit of an advantage, because they can always claim, like, we're out of sight, out of mind. We're storing carbon in the soil, you don't see it. Biochar buried underground. And with Exaquest, we'll discuss a little bit more. There is an issue of nutrient recycling with Exaquest. Make sure you don't remove nutrients from ecosystems. And if you're going to store on the Earth's surface or on the ocean floor, you need to be sort of ecologically conscious about that as well. So let's get to Exaquest, hopefully briefly. I just figured I'd give a few data points about where we came from, my background. So I was a lawyer up until 2011, graduated law school in 2006, clerked for a federal judge. So I was like a typical lawyer, had nothing to do with science. And I just sort of had this epiphany in 2011 that, like, you know, I don't particularly enjoy what I'm doing. It's not particularly impactful on the world. You know, if I'd like to have any influence on this climate and energy problem, I really need to educate myself about it. So I went back to school, put myself back in your shoes as an undergraduate. So I went to City College of New York, got a second bachelor's in chemical engineering. And as a perpetual student, I was like, oh, let's get a PhD. So I went to Stanford for the PhD program. And my research was electrochemically converting carbon dioxide into things like fuels and chemicals, so methane, ethanol. So I've been thinking about CO2 for a long time. And I would say about 3 years into my PhD, I started questioning what we were doing and what we were claiming our research would do. Because in our research presentations, we would say that, I mean, we would show graphs from the IPCC of carbon emissions and getting to negative emissions and how we would be part of that. And I started running the math on that, and I just wasn't convinced. And it got me thinking about, well, what would it take to actually move the needle on solving this climate change problem? And that's what led to the Exaquest idea. Damien, I see some activity in the chat. Is it something I should pause and address?
One question is earlier about Daniel asked. Daniel, you want to chime in and I ask your question?
Sure. I just wanted to get your guys' thoughts on, we were talking a lot about different technologies that are going to mitigate climate change in the future. And I think that sometimes people will bank on these technologies, and in the back of their head, they're just thinking, oh, I don't need to worry about climate change. We're going to figure out something that's going to do that in the future. So do you think people use that as a justification to be unsustainable and not care about the environment?
Absolutely. Yes, this is a huge problem. It's if you want to dig into the literature, just look up the keyword moral hazard. It's this idea that if we're banking on removing CO2, well, like you said, we don't have to change anything about how we're living right now. If you wanted to be cynical, you can kind of attribute that motivation to Microsoft and Amazon and their sudden interest in this topic. There's definitely a whiff of greenwashing about everything that they're up to, in my opinion. So it's a tricky one. I mean, I think, my initial slide about not being optimistic about reducing CO2 emissions and solving the problem that way, that's just me being realistic. I see a lack of ability on the part of humanity to restrain itself, right? We're asking people to restrict their consumption and live in a different way. And maybe technology makes that easier, but for the moment, it's not happening quickly enough. So that's a good thought to keep in mind. I would urge everyone to just really think hard about that, because if we give up entirely on reducing CO2 emissions, we're not really helping ourselves, right? So don't take my realism as like a call to just be completely cynical and fly everywhere and like that. You really should try to, restrain yourselves a bit. Any other questions?
Oren, you want to ask your question?
Yeah, sure. I had a question. I was kind of thinking about in the future, if we wanted to actually combat CO2 emissions and climate change, how would we ensure that we're actually focusing on the climate change itself and not like having elected officials focus on other purposes, like making themselves look better or for financial purposes for themselves?
I think this is a major problem at the moment. Right now, they're mixed up, right? And I would say most of the resistance on the right-hand side of the political spectrum is this belief that the Green New Deal and all this climate activism is a stalking horse for socialism. We're just going to like tear down the capitalist world and rebuild some socialist paradise. You might laugh at that, but serious people think that way. And I think the only way to deal with that issue is to just hammer on the results. Like go back to the Keeling curve and the annual plot of CO2 emissions over time. It's like, that's what matters. If you're moving those needles, if the Keeling curve is flattening out, if we're actually reducing CO2 emissions every year, then we're solving the problem. How we go about it, it's interesting. Everybody's afraid of like creeping socialism, but the truth is everything that's going on right now in the investment space for negative emissions is 100% capitalist. Like everybody wants to get rich doing this, and so they are not counting on any kind of socialist intervention at all. So I'll leave it there.
Cool. Okay. Well, yeah, chime in the chat more or interrupt her and keep going, John.
Okay. So yeah, I was at Stanford. If any of you guys do a PhD, Damien, you probably sympathize with this. It's like you hit a point where you're kind of like, what am I doing here? And you think a lot. You get, as a PhD student, get paid to think, basically, which is great. And so 2018, 2019, I was being completely unproductive on my own research. And I was thinking about this. And I was talking to people at Stanford and developing an idea. And over the course of that year and a half, reached three conclusions. One is that although this idea is not new, I can't take credit for inventing what I'm going to suggest. No one's seriously working on it. So it's just not part of the menu of options that people are researching seriously. I would say that leads into conclusion two, which is that scientists, businesses, and governments don't seem to be ready for an idea like Exaquest yet. And I just think it's a matter of time before I think it was Oron asked his question. I think they need like 10 or 15 years of seeing the Keeling curve skyrocket a little bit more before they start realizing that we need bigger solutions, more ambitious solutions. And then because I wasn't attracting any VC interest or anything like that, we still need to raise money for things. So 501c3 nonprofit seemed like a good option. So we founded that. Justin has experience working with nonprofits. Amber Yonda is actually Dr. Amber Yonda, who works for the Clorox Corporation. I knew her from my time at Stanford, and I got them to believe enough in this to sign on as directors. And we got our 501c3 status from the IRS a few months ago, and so that's where we are right now. Okay, this is the fun part. So on your right, you're looking at a pretty standard figure of the terrestrial carbon cycle. Terrestrial meaning it's happening on the Earth's surface, so we're ignoring the oceans for a moment. And all I want you to take away from this figure for the moment is the fact that the carbon cycle is mostly in balance most of the time. So photosynthesis takes in this 120, that's 120 gigatons of carbon. In terms of CO2, that's like 450 gigatons of CO2 per year is being sucked in by plants, from photosynthesis. Now, about half of that will make food that the plants consume, and then they use that food that re-emits the CO2. So that's called plant respiration. And then the other 60 gigatons of carbon is various decomposition processes. So we're talking about bacteria, funguses, decomposing things. And so the net result is that the carbon cycle isn't really changing. It's in equilibrium more or less every year. But in the background, there are these huge fluxes of carbon dioxide that are happening. So the idea is that plants and trees are using photosynthesis to capture CO2. It turns into biomass. That's happening on a huge scale. That carbon is stored. It's stored as well as direct air capture, any of these other technologies. It's stored as long as it doesn't decompose. And so the real idea here was that nobody's really focusing on decomposition. So that's what we want to do. And then, as I mentioned, these decomposition processes are happening on a huge scale. Our website says that it emits 5 times more CO2 than all of humanity every year. And that's where this figure is coming from. It's coming from this carbon cycle figure. So what we're proposing to do with Exaquest is to minimize the decomposition of stored biomass, and then looking at the life cycle of all CO2 emissions, just minimize any additional carbon emissions from anything else we do. So we're going to maximize net carbon storage. Okay, so let me repeat that with a simpler figure so it kind of sinks in a little bit better. So as I said before, you've got this huge CO2 uptake every year going into plants and trees, 440 billion tons of CO2. And then about half of it is plants consuming organic compounds for their own energy, and another half is decomposition. So this, your carbon cycle is roughly in balance. What we're proposing to do is to take some of this terrestrial biomass, there's a lot of it, and remove a significant amount of it every year, say 5 gigatons of CO2 equivalent, and then put it into storage of some kind where you could minimize decomposition. And our thinking is you can either do it above ground, and we can start working on that now, or underwater. And the underwater approach is very appealing because that's where the fossil fuels came from, right? You had biomass that was trapped underwater and under sediments became the fossil fuels. So in a sense, we're repeating how we synthesize the fossil fuels. And this next slide sort of hammers home on that a bit. It's what the solutions could look like, right? So what we can do today, we can certainly take dry biomass, put it in containers, and keep it dry. And I say dry because if you have anything, if you own any item of wood, you know that if it's dry, You could own it for 100 years, no problem. As soon as it gets wet, it will start rotting. It doesn't matter if it's pressure treated, chemically treated. Water and wood don't mix. It can't be wet for very long. And just to give you a sense of what this could look like in a practical sense, I did some calculations. This idea of a cone-shaped structure with a 200-meter radius, that's about a 31-acre footprint. That would store about 1.5 million tons of CO2 equivalent. You put a dollar value on that, that might be $30 million on 31 acres. Not bad. And then in order to run the storage system, and I can get into, if you're curious how you would do that, you can just slap solar panels on it, and that gives you a steady supply of a small amount of energy. I mentioned the future solution, this idea of burying biomass underwater. So these are literally figures describing for elementary school kids where coal comes from. So we're trying in some way to reproduce that. But there are some very sophisticated research questions to ask here, which is, one of them is, how do you densify biomass? Wood chips naturally float on water. You would prefer that they sink. How do you accomplish that? If you're going to bury wood chips underwater, what are the best conditions for that? Do you want to use sand? Do you want to use dirt? How deep? And then what you really want to avoid is methane emissions. So landfills are known to have a big problem with methane emissions. That comes from decomposition of biomass in the absence of oxygen. And so you could spend plenty of time researching how to minimize that.
John, can I ask you a question about that slide?
Sure, please.
So this is 1.5 million tons of carbon in the 31-acre facility.
That's right.
And so you were saying your potential, though, was how many gigatons?
I mean, when you're dealing with biomass, let's say 5 gigatons of CO2 is kind of like a global estimate. That's fairly common.
Okay. And the biomass, let's see, I suppose, did you think it was cheaper to put it above ground rather than to dig a lined pit, for example?
Yeah, this is a very good question. Actually, I'm glad we're getting to these things. So, okay, there's a couple issues with digging holes, right? You can certainly try to bury biomass. I would say there are 3 issues. One is that you're never going to keep water out of an underground system, right?
Okay.
Landfills have, even though they do their best to keep water out, water gets in. The second is that with an underground storage system, you're going to pay for every cubic meter that you create underground. You're going to have to dig it out, okay? And so that's not true with above ground storage. You just pile it up, pile up the wood chips or other forms of biomass, and essentially each cubic meter of storage is free. You just need to provide some kind of container to hold it. And the third thing relates to soil carbon, which is if you're going to dig holes on such a massive scale, you will be doing great harm to the stored carbon. If you're going to go down 100 meters, the amount of organic compounds you're going to disturb and expose to oxidation and decomposition is shocking. Like, you just really shouldn't do it. You shouldn't be digging that deep for no reason, if you don't have to.
Okay.
So,
and the solar is there just to keep it like a dehumidifier. Is that basically what you're doing?
Kind of. It would provide electricity, right? So, just like you slap solar panels on your house, you can use that electricity for anything you want. In our case, I think it makes sense to just run some air through the system, like just to dry things out, basically. The same way, like after you take a shower in a bathroom, you turn on the fan, and guess how quickly it gets rid of the water vapor.
Okay.
Similar idea. Okay, let's keep chugging here. But this is great. I actually like the questions because I think I think I'm addressing things that would be harder to address at the end. Okay, so you've seen this figure, this chart before. This was shown previously. Everything's the same as before. I just wanted to make 3 points about why we think Exaquest is a good idea from the physics perspective. You're relying on photosynthesis. So the cost of capture is essentially 0. I mean, obviously you have to go out and collect the biomass and then grind it up and move it somewhere. But those are different forms of cost. With direct air capture, you're paying an energy cost for every single molecule of CO2 that you capture. And it's different with Exaquest. I make the claim that storing CO2 in solid biomass is a good approach. In fact, if you were a laboratory chemist and you invented a device that grew essentially spontaneously with light and water and just some trace nutrients like nitrogen, phosphorus, and sulfur, and it spontaneously formed wood, you would win the Nobel Prize like 5 times in a row. Like, it's an amazing discovery. Photosynthesis would be. And so I think we tend to devalue how amazing it is. And in my PhD research, I was part of a research center called the Joint Center for Artificial Photosynthesis, this idea that we were going to beat nature at its own game. My major conclusion after 4 years of that was that I don't think we will, and we probably shouldn't. I mean, we can keep trying, but if we need a solution now, we should actually go with natural photosynthesis. And then the third point I would make is that, compared to soil carbon or forests, Exaquest is a more permanent form of storage. So you grow a forest, but trees eventually die. And right now we make no provision for trees dying. And you stuff organic compounds in the soil, and we just allow them to decompose. So those are some weaknesses in those other approaches. These other factors we spoke about. So you have profitability. I can get into the actual costs, but if you want to see the breakdown, when I applied for a grant at Stanford, I had to respond to some reviewer comments about this, and we actually broke down the costs of Exaquest's process. It worked out to be as low as I thought it would be. And there is the possibility that we could generate revenues from this. So, for example, forest thinning in California is a huge issue, right? We want to be taking trees out of the forest so that our forest fires are less intense. The reason that isn't happening is because nobody gets paid to do that, and I think there's a potential to, say, go to an insurance company and say, I'll remove 10,000 tons of wood chips for you. You just have to pay me, and you'll get the benefit back from lower insurance claims. Technological breakthroughs. Really, everything I've described is just about smart engineering. We're not asking for new inventions. And as far as ecological impact, I'll explain in a second how we would recycle nutrients. It solves one problem. We'd also have to collect what are called VOCs. Those are volatile organic compounds. The reason you need to collect those is because they would form smog if you just emitted them in the atmosphere. And as an example of a volatile organic compound, the smell that is in a pine forest, what you're smelling is a sort of the volatile organics that are being emitted from trees. So things like that, which could have some value.
John, and just as a heads up, we have about 5 or 10 minutes left.
Great.
So,
okay, and we're getting close. I think we're very close to the end here.
Perfect. Okay.
Minimizing the impacts of storage. So yes, I'm happy to speak about those some more, but think, for example, the 31-acre example that I gave on the previous slide. Compare that to some of the solar installations that are being put in California now. I believe the most recent one in Southern California was 2,000 acres of solar panels. So 2,000 acres, admittedly, it's kind of low value land in the desert, but that's all just being set aside for reflective panels, to generate electricity. So in terms of scale, our impacts may not be as great as you think they are. Okay. And I think this is a good place to kind of wrap up. You guys sent some questions to us. A lot of your questions are about the website. I deeply apologize. Our website sucks. It's terrible. But we're also extremely early stage, and we're not really promoting ourselves much at this point. So that's our excuse there. But these were some of your questions that the students actually asked. So one person asked, how will they decide where to extract biomass? Are there easy places to start collection? And the answer is yes. Obviously, in your own yards, we're talking small scale biomass, but it's enough to fill up lots and lots of bins. Construction sites generate a lot of wood. And this is, if you're building something out of concrete, the first thing you do is build a wooden frame so you can pour the concrete, and then they discard the wood when they're finished. Forest thinning is something I mentioned. And then something else you guys could look into is, this is related to climate change. Tree mortality is on the rise. So in California, we had the problem with drought coupled with the pine beetle, bark beetle problem. That killed 140 million trees in California, and those trees have not been removed. They're just sitting there. In some areas, 60, 70% of the trees are all dead. Okay. Somebody asked, where's the bulk of terrestrial biomass coming from? I would say in what we're familiar with, forests are the most concentrated place to get your biomass. I would say if you want to think about this, look up the concept of net primary productivity. That's NPP. And that's essentially the technical term for the rate of photosynthesis. And what you will see on the global map of NPP is that photosynthesis happens in the tropics at like a shockingly faster rate than in California. So yeah, geography, you know, there are places where there's more biomass. Someone asked which method of avoiding biomass decomposition is more efficient, above ground or underwater? Our answer here is that underwater storage is simpler. You don't have to dry the biomass. You don't have to build a complex storage structure. You just have to get it to the bottom and bury it and keep it there.
When you say underwater storage, Hannah is asking if you mean under the ocean floor.
Ocean floor is a possibility. Yeah, in fact, I don't want to say it's the only possibility, but it's, you know, the oceans are 2/3 of the Earth's surface. So yeah, it's likely some portion of the ocean floor, which by the way, is where all fossil fuels came from, right? So biomass went to the bottom of some kind of body of water. It was covered and it stayed there for millions of years. So yes, people will become sensitive about disturbing ecosystems on the ocean floor, but maybe there's no way to avoid it. Was there a question?
No, that was a similar question to about how do you accommodate the fact that clearing forest would help forests, may hurt wildlife in the forest. I guess it'd be the same kind of response, that it's a trade-off.
Same kind of thing, but you know what? I would say there are ways in which we need to clear forests. These are just imperatives right now. So anybody, you know, you were all around for the day of orange sky recently. I mean, that kind of level of forest fire is something we're not going to be able to live with in the future. And so there's a huge drive to get that under control. And the truth is, we'll either remove the trees ourselves or nature will burn them out for us. So yeah, but I understand there is a great concern about protecting wildlife and sort of respecting ecology. And I agree with that, because if you look at these other negative emissions technologies, you will see a lot of disregard for the natural world. Even in reforestation, you know, it's like maybe some areas aren't meant to be forests, and there's this belief that we're going to impose that. So
I want to add on to what John just said. Something that we talk a lot about is we need to be careful not to mistake ourselves for environmentalists.
Yeah.
And we're really looking at an existential threat to mankind. And while the environment is incredibly important to the here and now, we're really thinking about a bigger picture. And that means that we can't always be the best environmentalists. So we're careful not to call ourselves environmentalists. But
I'm a part of a Google group of scientists that discusses these issues. And also something that they're starting to bring up in their discussions is this notion that no approach is perfect. This is sort of what I meant by ecological impacts of these gigaton scale technologies. There are impacts of humanity on nature now. I mean, it's shocking what we're doing in terms of deforestation, industrial agriculture. And so we're trying to remediate that, but it's not going to be perfect. And so really all you can hope for is that we're going to respect nature as much as possible. But doing nothing is not respecting nature. Like continuing to do what we do now is hugely destructive. So that has to be considered. Okay, and I'll just add that like if we tried to do underwater storage right now on the ocean floor, Justin and I would be arrested. It's illegal. Like there is a huge amount of like legal restrictions on what you can do in the oceans, and political restrictions. It's not practical at the moment. But that doesn't mean we're not going to research it. And let's move on to the last slide. This is the last slide. So this is sort of the meat of it. It's like you guys asked what technology is being developed to help minimize biomass decomposition. And this figure here on the left is a simplified version of what it might look like. And it is extremely simple. You know, this cylinder shaped thing is just a theoretical container. If I had my choice of materials, I would use all the waste plastic in the world that's not being used for anything else. It just gets dumped and it goes in the ocean. Take that plastic, sort of melt it together and just make walls, right? Super cheap material. It doesn't have to be very sturdy. Imagine you're going to put a sheet of plastic into a pile of sand, right? It doesn't have to be the strongest stuff in the world. It just needs to provide a barrier to water, essentially. And then there's this idea that you could pass air through the system, right? So just run it through a filter beforehand, make sure you dehumidify that air, make it nice and dry, run it through your pile, you suck out your water and your volatile organics, and on the way out, it goes through another filter, and those filters can be regenerated just by heating them up, essentially. This is just, one flavor of the technology here. And then you ask, how are they minimizing their environmental and economic costs? How do they recycle nutrients? So what you're seeing here are the process steps. We'd have to collect biomass and transport it. Obviously, you want to minimize CO2 emissions there. At some level, you have to grind it because you can't be dealing with sticks and branches. You need to turn it into kind of a material that you can move around more easily. And then as far as recycling nutrients, this is where I'm going to go a little into chemistry for a second. Wood is extremely low in nutrients. And by nutrients, I mean nitrogen, phosphorus, sulfur, calcium, potassium. So these kinds of things. It has very little of it. Most of your nutrients in a plant are in the green part, the leaves and the stems, the flowers, that sort of thing. And another interesting thing about plants is that they have a high water content. So we're talking like 70, 80, 90% water. That's what a plant is, or a tree. And so if you take the green biomass and you grind it up and then you squeeze it, what you end up getting is most of the nutrient content because it's in the form of proteins, of phosphates, calcium ions, potassium ions. Those are all water soluble. It comes out in the water. And so that's really your simple technology for recycling nutrients. That's been shown to separate something like 60, 70% of the nutrient content without really any optimization or research. So that's a good start. And then drying, if you want to dry without CO2 emissions, the obvious approach is to use solar energy, so sunlight. And so you could imagine something like Exaquest working extremely well in a very hot, dry place. You just throw your wood chips out, let them get bone dry, and throw them in containers and put them in the Nevada desert. You could run a railroad from the Sierra Nevadas into the northern Nevada desert, and that's just as easy as it gets. Not all geographies work that well. And the reason we emphasize slowing down biomass decomposition is something else about the carbon cycle that's very interesting is decomposition happens very quickly in places like the tropics. It happens quickly in places where photosynthesis happens quickly. And by the same token, decomposition and photosynthesis happens slowly in places like California, where it's drier. So you don't have to stop decomposition entirely. You really just have to slow it down. So in a place like Brazil, you could collect a ton of biomass. You might not be able to store it for 100 years, but if you store it for 10, I guarantee you're slowing down decomposition a huge amount. So just something to keep in mind. But that was all I had. So
great. Yeah, I think we're essentially about one more minute left. So I think what I'll do is say that John and Justin can just linger for a few minutes if people want to linger on and ask any additional questions. I know John had one we didn't get to. Otherwise, just join me in thanking our two guests, and I'll collect the information for later. I'll post them their slides later, but I'll just join me in thanking them right now. Cool.
Well, thanks for inviting us.
Cool.
Thank you.
And,
Thank you.
Thank you.
Thank you.
Thanks.
Thank you.
Thank you.
welcome. And, we'll let you know when this website is better. I'd be curious if we have any success in improving it.
Cool.
I have a follow-up question.
Sure.
I'm no expert in this. I'm just curious. So if you were to sink biomass into the ocean, is there a possibility that it could impact like the marine marine carbon pump in any way?
It's an interesting question. So naturally, you may or may not know this, but there's already, like you referenced, a marine carbon pump. So there's algae and plankton and obviously fish and other organisms in the ocean. What tends to happen is that a small amount of that carbon that's in the surface waters, it'll form these dense clumps and it will fall to the bottom. So I believe that's called marine snow. And so that's happening at a slow rate all the time. Now, if you disturb that and you say introduce like 10 tons of wood chips and you bury it under some sand, you are going to change the ecology of the ocean surface, or sorry, ocean floor a little bit. But I don't know how to describe it. It's like that will quickly get covered. You know what I mean? Like say in 100 years, I would say you'd have a hard time finding where you buried those wood chips, assuming they're still there. You know what I mean? Like nature kind of restores itself remarkably quickly. Now, I would say scientists say that the ocean floor is like almost like another planet. We know very little about it. But, you know, it's just, nothing's going to be perfect. Maybe if you prefer, we could find sort of like peat bogs or more surface areas where there's water and then sort of sediment that you could use to cover biomass. That's why peat bogs and permafrost regions are so important. It's because there's carbon locked in them, quite a lot of carbon. So this is why we're going to do research. These are a lot of open questions.
Okay, thank you.
Mm-hmm. Okay. And
Sam,
actually,
you want to jump in, Sam?
Yeah, I think that actually kind of leads into my question a little bit. I was just thinking about, based on past classes and some knowledge of that prehistoric carbon, obviously in fossil fuels come a lot from bogs and wetlands.
Yep.
And that we've lost a lot of our wetland area globally over the last, since the Industrial Revolution.
Yep.
Have you guys looked into at all possibly trying to create artificial wetlands out of this carbon capture?
Neither I nor Dr. Yanda or anybody involved with Exaquest, we're not experts on these wetlands or you know, the kind of biology that's involved in them. But I think you're absolutely right. I think this is kind of the direction we're going to go in over time. I think oceans are kind of they're going to remain a bit of an off limits area for a while. So if you're not going to be able to access the oceans, then you work with what's available. And I can totally envision, you know, there are so many areas of our country that were drained. So DC used to be a swamp, right? And it was drained to build the capital. There are many cities like that, areas that were artificially drained and could be reflooded. And those would be perfect. I mean, unfortunately, there's like human construction on top of those areas, but not everywhere. And I think you're right. This is a real opportunity. But it's really just about research and showing people that it can be done at a small scale, and you just go from there and you know, try to get people excited about it. So good question.
Awesome. Thank you guys so much.
Thank you.
Cool. See you, Sam.
How'd John do? How'd we do?
Very well.
Is that everyone's out? That's it?
Yeah, just the strong
Okay.
survive.
Okay, great. Yeah, sorry it went so long, but I guess
No, it's about right.
all of the digressions were good. I mean, it was great. So I'm gonna stop the share.
Yeah.
And I'll definitely send you these slides. There's nothing like proprietary in them.
Right.